Good morning, everyone. Today we're going to continue looking at the solution for differential equation, particularly the second order differential equation. Okay, we want to just focus on second order differential equation. So example, you can have y double prime plus 2y prime plus 3 equals to 0. Now this is second order because of the two derivative here. Okay, and equals to 0 here also means that we have homogeneous equation. So the other thing there, to solve this second order differential equation, we need to consider, so this is pretty much a quadratic equation. So we need to find the roots of this equation. The roots can be found by writing it in form of characteristic equation. Okay, so I can now write y, the third derivative as m power 3, the second derivative as m power 2, the first derivative as m power 1, and no derivative, which is m0. You see that the power decreases. Okay, in this equation here, y double prime plus 2y prime plus 3 equals to 0. So I can write m squared plus 2m plus 3. Okay, equals to 0. So you need to solve this equation. Okay, so to solve this equation, you need to find the roots. Okay, we need to find the roots. Okay, there are three cases. Okay, there are three cases that we have looked in the previous video. So the case 1, when you have different roots. Okay, such as m1 and m2. So your general solution will be in this form. c1 exponent m1x plus c2 exponent m2x. Now the second case is when you have equal roots, such as m1 equals to m2. So your general solution is given as e to the power of mx c1 plus xc2. Okay, and then lastly, we can also have a complex root. Okay, so I'm just going to write it here. For case 3, when you have a complex root where your m is in this form, alpha plus minus beta I. So your solution here will be exponent alpha x c1 cos beta x plus c2 sin beta x. Okay, so these are all the cases that we consider. Okay, this is a second order differential equation that we are particularly interested on. Today, we'll look at one example first, how to solve second order differential equation with initial value problem. So look at the initial value given here. In other words, what we want to do here, given that problem with the initial condition, we want to find this value of c1 and c2. Okay, so let's solve this first question here. So first thing, we got to find the characteristic equation. So I can write that m squared plus 6m plus 5 equals to 0. Now, writing this as 0, we can find the root. The root we can find by factorizing these two equations, such as m plus 1, m plus 5 equals to 0. So we have two different roots, m equals to minus 1 and m equals to minus 5. Okay, so the good part here, we know the initial, the solution for this root given as yx equals to c1 exponent negative x m1 plus c2 exponent negative 5x. Okay, put on the first condition, y0 equals to 0. So we have y0, c1 e to the power of 0 is 1, plus c2 e to the power of 0 is also 1, which is equals to 0. So we have c1 plus c2 equals to 0. This is the first equation here. Now we need to find the second, condition here. So for the second condition, let's write it first. This is the general solution. y1 c1 e negative x plus c2 e negative 5x. So we have x equals to c1 e negative x plus c2 e negative 5x. Okay, now differentiate this. You have negative c1 exponent negative x minus 5c2 exponent negative 5x. Okay, now putting into the second condition, y prime 0, y prime when x is 0 is 1, so I have negative c1 minus, this is also 0, 5c2 equals to 3. Okay, so we have, I'm going to multiply everything with negative, so I have c1 plus 5c2 equals to negative 3. This is the second condition. Okay, so now what we need to solve the first condition, this one, and with the second condition. Okay, so the first condition we have is c1 plus c2 equals to 0. So I can write c1 equals to negative c2 and put it into this equation here. So c1 plus c1, which is negative c2. So I have negative. What happened there? Okay, negative c2 plus 5c2 equals to negative 3. So I have 4c2 equals to negative 3, c2 equals to negative 3 over 4. Okay, so we can find c1. So c1 equals to negative c2, and we have obtained c2 equals to negative 3 over 4. So c1 equals to negative. So we have obtained c1 as 3 over 4. So since we obtained c2 and c1 here, we can put into our solution. This is our solution. c1 exponent negative x plus c2 e negative 5x. Okay, putting into the c1 and c2 values, you have 3 over 4 exponent negative x minus 3 over 4 exponent negative 5x. So this is your solution. Okay, if you are given an initial value problem. Okay, so let's move on to non-homogeneous equation. Okay, so before we start non-homogeneous equation, so let's see that. So right now, looking at second order, a2 y double prime plus a1 y prime plus a naught y equals to gx. So we know how to solve when gx equals to 0, which is homogeneous equation with constant coefficient. So these are the steps that you have learned. Now, when gx is not 0, we have non-homogeneous equation. Okay, so that's what we're gonna study next. So non-homogeneous equation, any function yp free of arbitrary parameter that satisfy the homogeneous equation. Okay, this is the higher order differential equation. It's said to be a particular solution of the function. For example, a straightforward task to show that the constant function yp equals to 3 is a particular solution of the non-homogeneous equation y double prime plus ty equals to 27. And why is that? Yp equals to 3 is a particular solution. So you can, when you differentiate this, you get 0, right? So when I differentiate this is 0. So when I have 9 yp equals to 27, 9 yp is 3, so 27 equals to 27. That's why we say it's the particular solution for the equation. Now, if y1, y2, yk are solution of the homogeneous equation such that for gx, okay, we know how to find this when gx equals to 0. On the interval I, yp is any particular solution of the homogeneous equation. Okay, so another word here, so when you have homogeneous equation, the general solution that you have obtained is yc. Now we're going to have another one called non-homogeneous equation. The solution for that we will have as yp. Okay, so this is the general solution. When you have a non-homogeneous equation. Okay, yc here you obtain from the non-homogeneous equation that you looked on earlier on. And yp is called the particular solution. So you have a complementary function of yc and particular solution for the non-homogeneous equation. That's how you get the general solution for non-homogeneous equation. See, such as this, y equals to y1, yc, this is my yc, the complementary equation, and up to here, this you obtain by non-homogeneous equation, where you have 3 characteristic cases for the characteristic equation, and this is the one we call it particular solution for non-homogeneous equation. Okay, so the complementary function is the general solution of the homogeneous equation, like I've explained. Okay, but the general solution for non-homogeneous equation consists of sum of the two functions. So yx equals to yc plus yp. We know how to find this. We have already studied this one. Now this is the one we haven't learned, and due to the time constraint I have, I think I am going to wait. I'm going to wait on how to find the solution for non-homogeneous equation on my next video. Okay, so stay tuned, and we'll see you in the next video. That's all for today. Bye.